In part 3 of lecture 2, we will take a first look at finite automata. We'll start a discussion with the definition of deterministic finite automata. A deterministic finite automaton is a 5-tuple. In other words, it's defined by 5 attributes: Q, sigma, delta, Q0, and F. Q is a finite set of states. While Q might be large, it is still finite. Sigma is a finite alphabet. Q0 is part of Q. It is one of those finite set of states, but it's the initial state where we will always start looking. F is a subset of Q. It is the set of final states. While in theory, everything in the set Q can be in the set F, that typically is not the case. It would not be very useful were that the case. Delta is a transition function, and what we'll see is that given the state that we're in and the character that we are looking at now, we will go to one of the states in the automaton itself. Here you see an example of a deterministic finite automata. Q are the 4 states we have here: Q0, Q1, Q2, and Q3. Sigma is our alphabet. In this instance, just 1s and 0s. Our final state here is Q0, which is also our initial state. And below you see the values that we have for the transition function. The transition function has 2 parameters: the state that we're in and the character we're currently processing. Given that we have 4 states and 2 characters in our alphabet, that means we're going to have 8 different values. And you can see them here all laid out. The other thing you can see is that there are a few examples of regular expressions that this could accept. If I had 1, 1, 1, 1, it would take me all the way around until I came back to the start, which is the final state. The same would be true of 0, 0, 0, 0, although it would be going in the opposite direction. But again, it would come back at the end to the initial state, which is also the final state in this case. 1, 0 or 1, 1, 0, 0 would do something similar. These are not the only ones that I can have, but these are good examples of it. Here you see another example of a deterministic finite automaton. You can see here my set of states: Q0, Q1, Q2, and Q3. You can see my initial state, Q0. My alphabet is A, B, and C, and I have a set of 2 final states, Q0 and Q2. And you can see here spelled out on the slide all 12 values for the transition function. Now, you'll notice a couple things here we didn't see before. You'll notice that when I am in state Q1 and the character I'm processing is B, I will return to the same state. So what this means is that I can have as many B's as I want without moving elsewhere. Now, I can have here A, and that'll take me back to where I started. I can have A, C, that'll take me to the other final state. A, B, C, and that'll also take me to the final state. Or A, B, 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 C, and that'll take me there too. I can also make a great deal of the A, and back and forth. This is something we'll talk a little bit more about as we move on. You may wonder, what do I need deterministic finite automata for? That's a reasonable question. If we look at this machine, we'll see a couple things very quickly. As I start off in Q0, I can handle as many blank spaces as I want, staying put until I find the first letter or the first digit. At that point, you'll notice I go either to Q1 if it's a letter, Q3 if it's a digit, and in either case, again here, I will continue going around and around as long as there are letters in the case of Q1 or digits in the case of Q3. If I'm in Q1 and I run into a blank space, I'm going to end up in Q2, and I can have as many letters or digits here as I want. If I end up in Q5, this is where I'm going to end up, and I can handle from here as many letters or digits or blank spaces as I want. And again, I'm terminating here. In the case of Q3, I'll keep going on and on until I run into a letter. And then I can have a blank, and then I can have more letters or digits, and so on. This allows me to take a string of characters and go through it and recognize exactly what it is that I'm looking for. A well-designed finite automaton can go through the stream of characters coming from text and look for the structures in that spelling that I'm seeking. Regular expressions will have an indefinite repetition of symbols in its accepted language. When we use the asterisk, as you see here, that means that whatever is before it, whether it's something in parentheses or an individual character, may appear 0 or more times within the string. In the first case, we have open parenthesis 0, 1, close parenthesis asterisk. So we're going to repeat the sequence 0, 1, 0 or more times. This can give us 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so on ad infinitum. In the second example, I have 1 asterisk, 0, 0, 1 asterisk. So I will have a single occurrence of 2 zeros, preceded by 0 or 1s, and followed by 0 or more 1s. So I can have 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, and so on. As long as I have a string of however many ones I have, 2 zeros in a row, and then another string of however many ones, it would meet the specifications for this language. The third example, I have in parentheses 0 plus 1, 0, and after the close parenthesis an asterisk. So I'll have either 0 or 1, 0, and I can repeat either one of them as many times as I want. So I can have 0, I can have 1, 0, I can have 0, 1, 0, I can have 1, 0, 0, and so on. The only thing is that I can have as many zeros as I want. But every time I have a 1, it must be immediately followed by a 0. In the next case, you'll see in parentheses 1 plus the Greek letter epsilon. In this particular case, it's followed by what we had immediately before. This means I can precede the 0 plus 1, 0 repeated indefinitely, a single 1, or I can simply have nothing before all of this. And you can see an example here. Epsilon stands for the empty string, meaning nothing, literally. I also have 1 plus 0, all in parentheses, followed by an asterisk, and then a 1, 0, 1. So I can have any binary value I want as long as it is finished with 1, 0, 1. In the next case, what we see is a dagger after the 0, the 1, and the 2. It should be by rights a cross. This indicates one or more occurrences. So we'll have one or more occurrences of 0, one or more occurrences of 1, one or more occurrences of 2, which would be the same as having 0, 0 asterisk, 1, 1 asterisk, 2, 2 asterisk. So I'm going to have as many zeros as I want, but I have to have at least 1. I can have as many 1s as I want, again, as long as I have at least 1, and as many 2s as I want, as long as it's more than 1. B asterisk, in parentheses AA, followed by an asterisk, C, means that I can have, for example, nothing. I can have B. I can have BBB, or however many B's I want. I can have however many B's I want followed by AA, or however many occurrences of AA I want, followed by however many occurrences of C, that as I want. Up until now, we have only looked at deterministic finite automata. These automata will make one move and only one move given a combination of a given state and a given symbol. Let's take a look at non-deterministic finite automata. A non-deterministic finite automaton can make 0 moves, 1 move, or however many moves as it's set up to have. Now, there isn't any difference when I leave Q0, the starting state, in the diagram you see here. On 0, I go to Q3, and on 1, I go to Q1. But as I am in Q3, if I have the next symbol be a 0, everything will be undefined at that point. Similarly, if I end up in Q1 and what I'm looking to process is a 1, I will end up in an undefined state. The fact that I can have undefined states, as you see here, makes this different than a deterministic finite automaton. Similarly, if I can go to more than one place and in effect be in 2 states, that also is a different situation. As it turns out, a non-deterministic finite automaton will have an equivalent deterministic finite automaton. Let's take a look at the NFA that you see in the diagram. I have 2 states, Q0 and Q1. When the symbol read in is a 0, I will go from Q0 and end up in both Q0 and in Q1 at the same time. If, on the other hand, I am in Q1 and the next symbol is a 1, I will remain in Q1, but I will also be in Q0. But if the symbol at this point is 0, there is no transition for it, and again, I will be in an undefined state. As you see it represented here, you'll see that when I am in Q0 and 0, I will be in both Q0 and Q1 at the same time. If I am in state Q1 and I have a symbol of 0, you see there the letter phi indicating an empty set of states. If, on the other hand, the symbol is 1 and I am in Q0, I'll end up in Q1. But if I am in Q1 and I'm processing a 1, I will end up again in both states. Let's take a look at what the equivalent 5-tuple will be. I'm looking for m prime equal to the 5-tuple q prime, sigma prime, delta prime, q0 prime, and f prime. q0 prime is the exact same as q0, but only q0, not including q1. The alphabet is the same. I now have 2 final states, Q1 by itself, but also Q1 and Q0 together because Q1 is a final state. My set of states must now include something equivalent to the empty set, as well as the 2 original states by themselves and together. Now that we have found the initial state, the alphabet, the set of final states, and the set of states for the equivalent deterministic finite automaton, let's specify the DFA's transition function. Since there are 4 states and 2 symbols in the alphabet, that means that there will be 8 values we need to determine for the transition function. For the initial state and the symbol 0, the state to which we transition is the dual state representing both Q0 and Q1. However, in the initial state, if the symbol is 1, the transition is simply Q1. For the state representing Q1 and the symbol 0, the transition is to the state representing the empty state, because the transition in the non-deterministic finite automaton for these 2 is undefined. But if here we have the symbol 1 instead, the transition is to the dual state, because in the NFA, we would have 2 transitions, to both Q0 and to Q1. For the state representing the dual state and the symbol 0, the transition is to the dual state, because we union the transitions from Q0 to the dual state with that of the empty state. If the symbol was 1, we would union Q1 with the dual state and have the dual state once again. Please notice that if we are starting in the empty state, it doesn't matter whether the symbol is 0 or 1, we will remain in the empty state. Once we have defined the 5-tuple, the set of states, the alphabet, the initial state, the set of empty states, and the transition function, it is fairly easy now to create the diagram that you see on this slide. A deterministic finite automaton and a non-deterministic finite automaton can be considered equivalent if their 5-tuples are equivalent. On the other hand, they can also be taken as equivalent if they accept the same language. That means that whatever strings one accepts, the other will also accept. Whatever strings one will reject will also be rejected by the other. If you take a close look at the NFA in this diagram, you'll see that I can either have a binary string followed by 2 zeros and then a binary string afterwards, or a binary string followed by 2 ones and then a binary string afterward. If you trace your way through this deterministic finite automaton, you'll see that it also accepts a binary string followed by either 2 zeros or 2 ones, and in both instances, a binary string afterward. The fact that this will accept all of the same strings as the non-deterministic finite automaton shown before means that these two are equivalent.